quite a bit of the work of many people over the last 5 years. Thank you.
Yeah. Hi, everybody. I'm very excited to be here. And today I'm going to talk about our work until now, our present efforts and those future plans. And I'm really honored to be the spokesperson for this awesome team led by Eric, that includes Rabin, Sunesh, Lakshmi, Anmol, Yahel, Omar, Manuel, and all the other tier members that helped us develop and deploy these technologies all around the world. I want to thank you all. I also want to thank the IR Berkeley lab. They graciously hosted us for long years there, so I want to thank them all. And I'm really honored to start and speak to the people which are really dedicated and are coming at 9 in the morning on a Saturday. I'm not sure, but I would have been here had I not been the presenter. So I'm really happy that I can talk to you. So I want to start by looking at the map of the world, where the area of a country is proportional to the internet users in that particular country. And this is representative of a phenomenon we all know, which is the digital divide, with high rates of penetration in industrialized countries and very low such rates in developing countries. And this is why the map below represents the wealth of the world. We see that there's a very high degree of correlation between the GDP of a country and the network penetration in that particular country. And this is because it turns out that it's actually expensive to deploy network infrastructure everywhere. Now, besides this digital divide in terms of countries, we also have a divide between the densely populated areas and sparse populated areas. In urban areas everywhere in the world, the mobile technology is booming. While, for example, in rural areas, such as the rural India in 2007, the net mobile penetration was only about 5%. And this big gap is because it turns out that it's very challenging to, in fact, deploy networking technologies in rural areas. Why? Well, because the potential users are, first of all, poor. So because of that, we need to have some technologies which are inexpensive in terms of equipment, in terms of the spectrum licenses, in terms of powering these networks, especially when power infrastructure doesn't exist, but more importantly, in terms of long-term maintenance of these networks. Now, another issue is that users are distributed over wide geographic areas and can be very sparse. So we need some solutions that are very efficient in bringing connectivity exactly where needed into few places which are far away from each other. Finally, the applications we're looking at, which are very relevant for development, telemedicine, distance learning, telephony over IP, and so on, are demanding in terms of performance. Therefore, we need to have some technologies that have reasonable or good bandwidth, at least intranet bandwidth, as well as low per packet delay, such that they allow for interactive applications. So, for all of these reasons, we look at Wi-Fi, Wi-Fi in long distance environment, because it has been a technology that has been booming so much in the developed world that it has become very inexpensive. Also, it operates in unlicensed spectrum, which is free. So, we can get a shelf network card, which costs a few tens of dollars, connected with very cheap directional antennas, and what we get is wireless links which can span many tens of kilometers, as we will show, which are cheap, less than $1,000 per link, including the wireless routers, network cards, antennas, and everything, free spectrum, and also hopefully good performance. So having this kind of long links, we can then take the network connectivity from the few cities that have it and then distribute it to remote places which really require it. Now, unfortunately, we can't use Wi-Fi just as it is out of the box, because it turns out that the Wi-Fi protocol, the stack of protocols itself that are on top of it, are not designed for long-distance operation. For example, as we use longer and longer links, the performance delivered over wireless links degrades. This is a graph that shows how the standard Wi-Fi loses its throughput as we have longer and longer links. Another problem is the fact that because long-distance links are susceptible to interference, external interference, this performance is unreliable. And it doesn't scale very well when we have very large networks featuring many hops, because it turns out that adjacent long-distance links, especially if operated on the same channel, would interfere with each other and making the performance degrade. On top of this, because of the nature of the experimental nature of the hardware platforms that we're using, the small routers and so on, it is also hard to maintain in the current state. So we wanted to use the potential of Wi-Fi, but then to solve all of this problem and bring the potential closer to where we want it. In order to do this, we did two things. We built and deployed WireNet, which is a solution that includes a TDMA MAC that replaces the CSMA mechanisms used by standard 8.11, and it also includes a suite of loss recovery mechanisms in order to make this performance reliable. Besides that, we also build a suite of maintenance tools that would allow for easy, sustainable maintenance of these long-distance networks. So what did we do in terms of performance? If we revisit the graph where we showed how the standard Wi-Fi degrades in performance, we see that in comparison, WireNet can maintain this over hundreds of kilometers without degrading and operate in maximum throughput. And this is experiments with real cards that we performed. What we haven't shown there is the fact that also our loss recovery mechanism can be very effective in making this performance reliable, and the fact that our protocols avoid the interference by synchronizing the radios together, and therefore allowing us to operate on the same channel on several adjacent links, be more spectrum efficient, and be able to seamlessly scale the size of these networks as much as we want. In order to show that we can go the distance, we went ahead and used WireNet to deploy a 382-kilometer link in Venezuela, which is a world record, by the way, of the longest unamplified Wi-Fi link, where we show that WireNet can achieve as much as 6 Mbps over 8.11. Now, what did we do in terms of maintenance? Well, several things. We built better power solutions that include a smart charge controller that allows, that's inexpensive, that allows for efficient solar-based or wind-based power solutions. We also built a set of remote management tools in order to allow us to diagnose and fix problems from far away and allow the local staff to do the same. And we train the local staff in order to enable them to independently maintain these networks with the knowledge that they have. So all of these components were really essential in allowing us to, in the end, deploy networks which can run for years and then can be sustainable. And the best example of this is the Aravinda Hospital network that Suresh has discussed in detail yesterday, which is a network that has worked for years now, serving many thousands of patients, but more importantly, a network which is sustainable both financially, paying for itself, as well as operationally, meaning that the local staff now have enough knowledge to maintain and extend this network on their own or with very, very minimal help from our part. So this is what we did until now. And in the following I'm going to discuss about what we're going to do and what are we currently doing. And what we're doing is to try to be smart about various things. First, we want to be smart about time and time management. So it turns out that the one main drawback that WireNet had was that it was using a fixed schedule and of transmissions on the links, which was disregarding how much traffic we had and in what direction. So in order to fix this, we built another protocol, JazzyMac, which is really inspired from WireNet, uses the same mechanisms, but it has the main issue, the main improvement that the transmission slots are locally adaptive according to the traffic demand that we see, and we enable this together with interference avoidance by introducing a novel concept which we call timestamp tokens, which I'm not going to discuss in detail, but I would be very happy to discuss this thing with whoever is interested. So our initial evaluations show that JazzyMac would allow us to increase the maximum throughput of WireNet by 50 to 100% in large networks, but also to decrease the end-to-end packet delay in these networks by 2 or 3-fold at the same bandwidth, which is quite remarkable. So we're really excited about deploying and playing around with this new version of the Mac. Now, another thing we want to do is to be smart about space and smart about direction. So one way to reduce the cost of these deployments is to allow for relay points and network nodes to, instead of having n radios and n antennas directed in various directions, instead to have one radio and an electronically steerable antenna that would very quickly and dynamically point exactly in the direction which we require, which would then enable to have much smaller costs for these deployments. It will also, this is one example where we have one transmitter which would very quickly be able to steer and point to two different clients. Now, this would also help us with deploying these networks easier, aligning these directional antennas easier, because we don't actually require alignment, and because of that we will basically spare Melissa and RJ from acts of heroism going up and manually aligning all of these antennas. It's going to be done automatically. This will also enable us to much quicker and easier deploy large-scale networks. And finally, last slide, we also want to be smart about frequency and smart about coding, which is something we weren't able to be until now because the hardware platform didn't allow us to. But now the new Atheros cards allow us to use smaller channel bandwidths than the ones used by the standard Wi-Fi, and this would be very useful because it turns out that if you use a smaller channel bandwidth, then the level of noise that you see over that bandwidth is also smaller, and because of that we can increase the signal to noise ratio of our links and increase the range, make them even more reliable, and so on. Dividing the spectrum would also allow us to have many more simultaneous transmissions. And finally, we're also investigating using co-division multiple access, which is again something that we can do now because we're collaborating with MIT and programmable 8.11 platform, which has recently become available and which will allow us to hopefully be even more optimal with these types of solutions. And with this, I'm going to, one more thing, which is actually very excited on the deployment in terms of deploying new networks. We would actually want to take network connectivity across the Gibraltar Strait and bring it all the way to the heart of Africa by building a wireless backbone featuring many links. It's a simplified map of this, but this is something we're really excited about doing right now. And with this, I want to open it up for questions, and thank you very much. Yes?
The steerable directional antennas, is that accomplished mechanically, or is that
No, it happens electronically and very quickly by shifting the phase of various, we have basically several antenna components that will operate at different phases, and by shifting the phase of the signal there, we can effectively create directional lobes in various directions. And I don't know whether you had a chance to see a demo. We have a demo working. Omar and Kevin put it up yesterday in the demo session where we show how such an electronically steerable antenna works. Sure.
Do you happen to know if anyone is doing anything like this in Haiti?
In Haiti, I'm sorry. Unfortunately, I'm not aware of that. I know that there are many people that are playing with long-distance Wi-Fi, not necessarily WildNet, just simple long-distance Wi-Fi as it comes out of the box in many places around the world. So it's quite possible that this happens in Haiti, but we haven't looked explicitly at that.
So with the steerable antenna, when another node comes into the network, does it automatically detect that node is there, or do you need to do some other configuration?
Well, there are several ways to do this. Typically what happens is that you have initially some sort of a training phase where nodes are in the discovery mode, and then we are going to collaborate to find what are the best phases to use in order to increase the signal strength between the two nodes. So the best way to do this is to periodically have some discovery phases where then we would be able to accept new nodes in the network, but it's not necessarily something that's being done on a regular basis, or continuously.
Question?
Yeah, have you considered this a software radio idea? It's kind of a programmable radio, if you want to.
Yes, so luckily we're able to collaborate with Hari Balakrishna's group in MIT that have prototype some software programmable platform for 802.11 specifically, and we have some good ideas about how to use this to increase performance even further, and not as much in the point-to-point long-distance scenario, but then in the next step, which is also required, which is once you have the connectivity into one place, have point-to-multipoint technologies that can then efficiently distribute this connectivity to, say, many places in one particular village, and do this efficiently.
Is there any maximum known range on an omnidirectional antenna for this?
Well, the problem with omnidirectional antenna is that you have very small gains, a few dBs at most. Because of that, you see that standard Wi-Fi access point can go no longer than maybe 1 kilometer, even if it transmits at full blast. So the main innovation here is really using directional antennas or using steerable antennas that can increase the signal strength enough in order to increase this range even higher. So we're not really doing much more than that on the signal strength side of things. Just using directional antennas or steerable antennas is what guarantees the range. And then we're making MAC protocols that have the right timing and synchronization in order to take advantage of this range.
What type of angles do you get on your antenna? Because you'll still need a number of antenna because they're not omnidirectional.
Right. So that's why most of our links are very highly directional links. For example, the 24 dB directional antennas we're using have an angle of 8 or 6 degrees, depending on vertical or horizontal polarization. And right now, the prototype for the steerable antennas has a much wider angle because the signal strength is lower, a few tens of degrees. But as we add more elements to the steerable antenna array, this is an array of smaller antennas, as we come to 64 elements, which is something that we're going to do in the near future, then we're able to have really very directional beams that have a very small width of a few angles, but that an angle that can be very quickly then switched from one client to the other dynamically.
Yes, in terms of signal strength, then, does that increase the power requirements for the system? Do you need...
Having a steerable antenna?
Yes, for a higher signal strength, you need a lot more power, or just a...
No, it doesn't. So right now, we have passive antennas, which are directional, and which work fine for hundreds of kilometers if we use 24 dBs. And our prototype for a smart antenna will also be able to have higher than 20 dBs gains and be this and continue to allow this automatic electronic steering. So we really don't need, in terms of power, we're good, basically.
One other question on the last slide that you had, the transmission across the Africa there on the west side. Are you line of sight? Does this have to be line of sight transmission?
This has to be line of sight transmission, and this is where the big problem occurs. How will you be able to do this over such wide distances? The biggest problem about line of sight, really, at such high distances, is the Earth's curvature. You know, if you have really flat terrain, just a field, then you need towers that are hundreds of meters tall in order to have a 100-kilometer link. But that,
high atlas here?
Sorry?
Yes.
Yes, exactly. We need to use mountains as high points, or we need to use some sort of valleys where you can just ping pong from one side of the valley to the other in order to take advantage of the natural conditions and continue to have line of sight in a multi-hop way.
Okay, excellent.
Okay, thank you very much.